Hey everybody, today I'm going to do some chapter 8 problems and work the ones out from the lecture slides, kind of go over some good strategies in solving these types of problems. And then on Monday, we will meet and review for the exam. So we did a few examples in lecture on Monday, and I think we stopped right about here. We went through the whole lecture, but we didn't do a couple of the examples. So I'm coming back to this one. All right, so we're dealing with collisions, applying the conservation of momentum. And in this example, we have two gliders with different masses, and they're heading toward each other. After they collide, we know some final velocities, and in the picture, we're given their initial velocities. So the question is, what's the final velocity of A given the final velocity of B being 2 meters per second? And how do the changes in momentum and velocity compare to each other between the gliders? So we're dealing with collisions, so we know that we're going to be dealing with the conservation of momentum of the system, right? So this is a system of two objects, glider A and B. So the total momentum of this system initially, and momentum is a vector, is going to equal the total momentum of the system in its final state, which would be after the collision, right? Be initial and final, before and after collision. So we kind of know almost every piece of information, right? So you kind of look at this picture, you know that momentum is mass times velocity. You're given 3 out of the 4 velocities. So you should be able to find the 4th velocity pretty easily, right? Because you have all the information, you only have one unknown. So it's a really good habit to kind of like take a step back and look at your problems, like big picture. What are you given? You know, what types of quantities are these, and what's missing? So let's go ahead and write out the total momentum, right? Mass A, initial velocity A, mass B, initial velocity B. You know, my subscript naming system might be a little different than yours, and that's okay. This is just how I read it. Oops. Okay. And this is all one dimension, so I don't need to include any subscripts for X, Y, or Z, right? This is all the motion is going on in the X direction here. So let's go ahead and write out everything we know into the conservation of momentum. Make sure we include the correct signs for the velocities. This is where everybody messes up. If you're going to mess up, this is probably where it's going to happen. So don't. So don't do it. Put a number here for the mass. All right. It's pretty easy to solve for the final velocity here, right? Wait, minus 0.3 times 2. There we go. I kind of did everything in one swoop. One algebraic swoop. Okay, we have negative 0.2 kilogram meters per second in the numerator, divided by 0.5 kilograms. So that's going to be 0.4 meters per second negative, right? There's a negative sign here. So the glider A is going to be moving to the left, right? And does that make sense to you, right? Those things, if you envision those gliders heading toward each other, they bounce off each other, and they head back in the direction from which they came. And they're both of similar mass, right? 0.5 kilograms and 0.3 kilograms. They're not really that much different from each other. So you should expect this, okay? How does the changes in momentum and velocity compare between the gliders, okay? So let's take a look at glider A. His mass was the heavier, okay? And then let's look at glider B. His mass was slightly lighter. And initial and final velocities. Okay, initial velocity, 2 meters per second each one, right? They're both starting off with the same speed, but they have different momentum because they weigh different amounts, right? Or I should say their mass is different. So their final velocities, it's 2 meters per second for glider B, right? That's what we were given, 2 meters per second to the right. But the magnitude of the velocity, aka the speed of the first glider that's a little bit heavier, is not quite as fast, right? It moves at a slower rate to the left than its initial speed to the right. So the question asked us to examine their change in momentum and the change in velocity between before and after the collision for each object. So in other words, PA final minus PA initial for each. Okay, 0.5 kilograms, and then final minus initial. Okay, so we get a velocity difference of negative 4.2 meters per second. I'm kind of ignoring my kilograms right now, okay, just to kind of illustrate. So glider A has a larger velocity difference. Oops, 4.2. How can we understand that? So, forces cause changes in velocities, right? And so what force is causing the change in velocity of each of these gliders? Well, for glider A, it's the force of glider B on A, right? That force is causing glider A to accelerate. And for glider B, the force from glider A is causing glider B's acceleration, okay? And because these forces, I should have a subscript here. Because these forces are of equal magnitude, right? These are the forces that are the Newton's third law pairs that are responsible, for the change in momentum, right? The forces that are being added to cause an acceleration. They have the same magnitude. So what that means is these objects are going to have different accelerations, right? It's accelerations that depend on their mass. All right, these numbers are different numbers, right? This one's 0.5, this one's 0.3. These numbers are the same. All right, if we had a time, we would be able to calculate this using the impulse momentum theorem. But let's just say for now, let's say it's 5 newtons. 5 is my favorite, dummy number, right? They're equal magnitude, so they're both 5 newtons. 5 newtons divided by 0.5 is going to have a different acceleration than 5 newtons divided by 0.3. And in fact, this is going to have a smaller acceleration, right? Because we're dividing by a bigger number. This one's going to have a larger acceleration. Okay, we're dividing by a smaller number. And that makes perfect sense because look at the change in velocity as a result, right? Larger acceleration, larger change in velocity. Smaller acceleration, smaller change in velocity. Okay? So everything that we're learning is connected to what you have, studied previously, right? In Newton's laws. It's the same concepts, but we're just changing the discussion slightly and talking about changes in velocities and momentum versus accelerations and forces. So this is, an example of a type of problem that could appear on the exam for sure. Especially the end when you're comparing these, quantities, the properties of those objects that are colliding. That is, could appear in a conceptual form on the exam. So we did this example on Monday, and this was really highlighting the two-dimensional nature, or I should just say the vector nature of momentum, right? Momentum is a vector, and so from the conservation of momentum equation, right, which is a vector equation, you can actually create two equations from it, right? Conservation in the x and conservation in the y. In other words, the x components of the momentum initial will equal the x components of the final momentum, and same for the y's. We talked about two different types of collisions, elastic and inelastic, and the only difference between them is that for elastic collisions, you have the additional conservation law of kinetic energy, not total energy. Well, total energy is, most likely conserved depending on the situation, right? When is total energy conserved? It's conserved when you have no forces, external forces doing work, right? So as long as there is no friction, or if there is no dissipation of energy of any kind, or an addition of energy, okay, from a push or a pull, then you can definitely say that energy is conserved. But in elastic collisions, we're talking about kinetic energy being conserved, all right? So in inelastic collisions, the only conservation law that you can use is momentum conservation. So we're going to do some elastic collision examples as well as some more inelastic collision examples. So here's one of them. And so in this example, we have our two gliders, right? And now the gliders are equipped with springs, or not springs, sorry. Springs, if they're equipped with springs, then they would bounce off each other, right? And it would be an elastic collision. But in this example, which I think we're going to do coming up, in this example, they are, the Velcro is put on them essentially so that they stick together when they collide. So we're going to find the velocity of the group, the AB group, after they collide by applying the conservation of momentum. Oops. So this is using the previous example that we just did, the same parameters. Okay, glider A is 0.5 kilograms, glider B is 0.3. Initially, both moving with a speed of 2, but in opposite directions. So you're going to have a negative sign for anything moving to the left. And so we're going to write down the conservation of momentum, right? It's the total momentum, meaning the momentum of both A and B, initial plus or equals the initial, the final momentum of A and B. Wow, that was a terrible B. And since everything is in one dimension, this is all essentially subscript x, right? But we can drop that because we don't need to differentiate between x and y right now. So now we apply the conservation of momentum with our givens here in the image. .5 kilograms, 2 meters per second, plus 0.3 kilograms, negative 2 meters per second. That's going to equal the combined mass of A and B, which is 0.8. Times their final velocity, right? So I combined MAVAF with MBVBF because the final velocities are equal to each other, right? Because they stick together and are moving to the right. So now we can easily solve for VF. And when we do that, we get 0.4 kilogram meters per second in the numerator divided by 0.8. And that's going to give us 0.5 meters per second positive, which is to the right. Okay, which just matches the picture as shown. So now, we found their common velocity moving to the right. Let's examine their kinetic energies, okay? And to get an idea of like where the energy is going and how is it being transferred, and is this a collision that is elastic or inelastic? Like we can confirm that, right? Because I kind of cut it off here, but we can confirm that this is in fact an inelastic collision because the kinetic energies are not conserved, right? So let's compare initial and final kinetic energy of the system, right, of A and B. We did that in the previous example. So you could run over there and grab that value. It was 1 joule, okay, for Ka. Kinetic energy of A, and then 0.6 joules. That should be a B. Kinetic energy of B. Okay, so their initial kinetic energy together is 1.6 joules. Now, after the collision, they are going to be moving together at half a meter per second, right? So we're going to have 1/2 times their total mass times 0.5 squared, and that gives me a kinetic energy of 0.1 joules. Okay, so a lot of energy is lost, right? 1.5 joules of energy is lost in the collision. And where does it go? Where did it go? Where did the 1.5, right? Kf minus Ki is 1.5, negative 1.5 joules. Where did it go? It left the system of A and B, and it escaped as, well, you could think, right, because these two objects are now fused together, right? They're moving as one. So there had to be some molecular processes that, linked these objects together. And those linking processes cost energy, okay? One way to think of it is the objects collide and there's heat due to the collision. That heat melts stuff, and then when that melted stuff cools, you get the two objects stuck together. Okay, so it's just a couple ways to think about how it is that the energy disappeared after the collision. There's many ways to explain that energy loss, okay? But ultimately, it's because of those two objects being stuck together. And there's energy required to do that. So this is an inelastic collision, right? Because kinetic energy is not conserved. All right, we're going to skip the ballistic pendulum It's a pretty long and detailed problem, and it's one of my favorites, but I think, for the purposes of this fast-paced course, it's just one scenario that we're just going to skip for timing reasons so that you can really focus on the basics. And the basics that I'm talking about are very vector-heavy basics, right? Dealing with vectors. So this is going to be a momentum problem that is vector-heavy. And so we have two cars colliding. Okay, we have a collision going on. These cars are moving in different directions. So we're going to have an X and a Y, and we're going to have components in the X and the Y of velocities, okay, and thus momenta. So the car and the truck collide. They move together, okay, from the impact point as one, all right? What does that mean to you? That means that these two objects are stuck together and they're moving as one object in the very same way as example 8.7, right? Except now it's just occurring in 2 dimensions. So this would be a 1-dimension inelastic, if we're going to be inelastic, if we're going to be categorizing problems, which is a good strategy to make sure you understand what could appear on the exam. Categorize these problems. Make sure you can understand what it's asking. This is a 1-dimensional inelastic collision problem because the objects stick together. It's actually a completely inelastic collision problem, 1 dimension. This is a 2-dimensional inelastic collision problem. Okay, so let's tackle that. We're going to need to apply the conservation of momentum in the X and in the Y direction. Okay, so conservation of momentum is a vector statement, right? The total momentum of the system initially, right? This is a total value. It's going to equal the final momentum of the system. And that system consists of A and B, right? Mass A, the truck. Let's use their naming scheme. Mass truck, velocity truck, initial. Okay, and then this is a vector. Mass car, velocity car, initial, that's a vector, equals mass truck, final velocity truck. Mass car, final velocity. There we go. Right, these are vectors. So this is equation 1, which can be split into 2 more equations, right? An X statement and a Y statement. So now we can talk components, right? The velocity of the truck initially in the X direction. The initial velocity of the car in the X direction. Final velocity of the truck in the X direction. Final velocity of the car in the X direction. Okay? The subscripts get a little bit wild here. Let's clean this up. There we go. So let's write the same statement. For the Y's. And so now this is basically the 2 equations we're going to be working with. We need to find the final velocity, right? We're going to find the final velocity of the wreckage after the impact. So we're looking for these values. Well, we can actually clean this up a little bit. Why? Because the two vehicles are going to be traveling as one object, right? And in the final moments after their collision. So we can actually erase all of this here. Okay. And that's going to really reduce some complexity in the problem. We're going to have mass of the truck plus mass of the car times their final velocity in the x. Mass of the truck, mass of the car equals their final velocity in the y, right? So that takes away two unknowns, essentially. So, so now let's write what we know about the situation, our knowns. Okay. The truck and the car and their initial velocities in the x and the y. Okay, what we're looking for their x's and y of their final velocity, right? So truck moving to the right 10 meters per second, positive x direction, 0 y direction. What about the car? The car is moving north, so it has a positive y component in the velocity, no x. 15. Right? And then their final is going to have some x and some y component, which is what we're looking for. So now we can plug these values in here, right? This is 0. And just to keep track, we're going to work on the 2x equation. So the mass of the truck is 2,000 and the mass of the car is 1,000. And then so their total combined mass, 3,000. And then looking for unknown in the x, our unknown final velocity in the x. So we have everything actually to find that unknown value right now. So let's get it. It's going to be 20,000 divided by 3,000. Okay, 6.67 meters per second positive. Now we can get our y. And so we are going to have the car moving, no truck motion in the y direction, but the car is moving in the y at a speed of 15 meters per second, positive. And that's going to equal their combined mass times the y component of their final velocity. And so we can solve for that real quick. 15,000 divided by 3,000. So that's 5. Positive. So now we know the final velocity, right, of the combined mass of the two vehicles. It's going to have an x component and a y component. And you can see that that is pretty much what's pictured here, right? A velocity, a final velocity that's pointing in the first quadrant, positive x, positive y. So in order to describe this velocity, you can describe it in x and y, or you can give a magnitude, right, an angle. So the magnitude would be obviously 6.67 plus 5 squared. Which is about 8.33. Angle would be, tan inverse of y over x. 36 degrees. Makes sense. Right? So that's how you could report the velocity. Okay, as components or magnitude and direction. Okay, so that would be like north of east. Depends on how, in the exam, how it's phrased, right? Like what it's looking for. Could be asking for any of those. So it's right. You just, in this case, inelastic collision is probably the easiest of the two. We're going to do an elastic collision coming up in a minute. 2D gets a little confusing because you need to make sure you got your X's and your Y's separate, right? It takes a little bit of extra time being careful in your organization, like I just did, okay? Making a table, writing things down, okay? You don't want to accidentally write the wrong thing down, the wrong term down, because you're being messy. All right, so let's look at some elastic collision. So we're going to do an elastic collision problem now, and you might recall that there are some special equations that can be used to solve elastic one-dimensional problems. So let's scroll up and recall those. Two of them are listed right here. These are basically found by solving the conservation of momentum and conservation of kinetic energy equations simultaneously for the case when one of the two objects is at rest. Okay, so it's a special use equation, formulas, right? These are special use. One-dimensional elastic collisions, one object at rest, okay? Then the third shortcut equation is this one right down here, okay? The relative velocity equation. And so this relates the change in velocities of the objects, okay, before and after the collision. And so we're going to take this and we're going to use this in our next problem. And I'm going to show you why we're going to use this one and not the other two. Okay, so I'm going to copy and paste this guy right here. We're going to need it. This is our next example. So we're going to have our gliders again that we just looked at in the previous example. So same masses, same initial velocities, but now we're going to attach some springs. Instead of Velcro, we're going to put springs on it. And what's going to happen is when these objects collide, they'll bounce right off each other, okay? And there'll be no loss in energy, kinetic energy, when they collide. Essentially, right, the springs are just going to bounce those guys right off each other. So the conservation of momentum definitely applies, right? Initial momentum of A plus initial momentum of B, and these are vectors, right? Final momentum of A, final momentum of B. But since everything is in one-dimensional, everything's going to be in the X component, right? So we can leave it all kind of written without vector notation. So the initial momentum of those two objects, I think we had a value from the previous, right? Let's just write it out again. It's 0.5 kilograms, 2 meters per second to the right, 0.3 kilograms, and then negative 2 meters per second because he's moving to the left. And then that's going to equal their final momenta. So that's where we see, in the previous example, we had only one velocity, right? Because they combined together and became as one. But now we're going to have two unknowns. We're going to have a final velocity for A and a final velocity for B. So we have one equation, two unknowns. We need a second equation, right, to help us solve. So we need second equation. And so what second equation are we going to use? Hint, hint, we're going to use the relative velocity relationship, okay? Now, there is another second equation that you could use. Because this is an elastic collision, you could use the conservation of kinetic energy. It's totally valid. Totally do it. Do it. Do it. And actually, I already did it. I'll show you the algebra that's involved, okay? So you could do that. All right, just a reminder, it's this equation, right? Equals, the final velocities squared, right? Summed together. I did that, and you get some nasty algebra. Using the relative velocity relationship is going to spare you the nasty algebra. And, let's just take a look at it. I wrote it out over here. Right here, I did it long way using the conservation of kinetic energy. And so what I did is I had those two equations, right? Conservation of momentum, conservation of kinetic energy. I solved equation 1 for one value, VBF, and plugged it into equation 2. And what that gives you is a quadratic equation, okay, to solve. So I'm basically, instead of solving a quadratic equation using the conservation of kinetic energy, I'm telling you your second equation can be the relative velocity equation. VB final minus VA final equals negative VB initial minus VA initial. Okay. Let me fix my subscripts there. There we go. So let's plug in our values here. We don't know VBF, we don't know VAF, but we do know VBI and VAI, which is negative 2 and 2, respectively. So we know that the difference between the velocities should be constant, which is 4 meters per second. So this gives us another linear equation with the two variables that we're looking for. Now, if we were to go through the conservation of kinetic energy, that would leave us with a second equation, sure, but it would have square terms, and that would cause, a lot of headache, right, with algebra and solving a quadratic equation. So that's why using the relative velocity equation, relationship is much smoother. So what we can do is we could just pick, we have equation 1 and equation 2. We can solve for VBF in one equation and substitute it into the other. So let's solve 1 for VBF and then insert that into 2. So as it stands, equation 1, I didn't fully write it out. It's going to be 1 minus 0.6, so plus 0.4 VAF. Okay, so let's solve for VBF. And then we will insert that into equation 2. I'm going to drop my units. All right, so this is, I inserted VBF right here. Okay, and that's what I wrote out. So now I'm going to combine all my terms. So I have 0.4 divided by 0.3. All right, so let's combine. Okay, we get negative 1 meters per second. So the the final velocity of glider A is going to be moving to the left at 1 meters per second. And we can use that to find what the final velocity of B is, right? We can take this very same equation right here that we found for VBF and insert what VAF is now. Negative 1, make sure you use your sign, right? And you're going to get minus a negative, so plus 0.5 divided by 0.3, 1.67, which is roughly 3, right? 3 meters per second. So the final velocity of glider B is going to be moving to the right by 3 meters per second. And you can kind of see those arrows, right? We have a arrow pointing to the left about magnitude 1, and then an arrow pointing to the right, magnitude 3, to indicate the final velocities of the gliders. So this is an elastic collision. And so the question, all that we wanted to know was the final velocity. So, and that's what we got. We took a little bit of a shortcut, right? And we needed a second equation instead of using the conservation of kinetic energy, which is certainly true for elastic collisions. We used a bit of a shortcut equation that relates the relative velocities of the gliders before and after the collision. So this is a great example of something that could appear on the exam. Okay, and if we wanted to categorize this would be a one-dimensional elastic problem. Okay, I won't be giving you two-dimension. There won't be any two-dimensional elastic problems. So the final problem I want to do is a center of mass question. I don't have an example here. I believe that my center of mass question is going to be in the textbook. There you are, textbook. And so I'll take this moment to point out, I've probably shown you all before, a section in your textbook that is, this is only physics 2. There we go. And here we go to the guided practice section. Okay, so in your textbook, I'm in chapter 8, right? And I'm looking at all the chapters in chapter 8, and one of them is guided practice. And in this guided practice, it looks, the formatting in the iPad version of the ebook is really tragic. But what you'll kind of see is, let me see if I can highlight it. There's going to be some problems here that are related to examples that we do. So you can see that there's 3 or 4 problems here, right? They start here at VP, right? VP 8.6.1, 0.2, 0.3, and 0.4. They're going to be similar to the examples that we've done. And this would be a great place to go to find additional, kind of worked examples. The examples related to the center of mass are right here in this section. So I'm going to do one of these problems. Oops. Here, let me turn this off. Okay, great. And I'm going to take a screenshot of a problem. Okay, that is an awfully strange screenshot. All right, there we go. So the problem we're going to do, we'll do the first one here, and these are the center of mass examples. Okay, we want to find the x and y coordinates of the center of mass of a system that is composed of the following particles. So you're going to want to draw your xy axis and locate those particles. One is at the origin. Okay, and so those coordinates are 0, 0. The second object, and so what's its mass? 0.5. So we're going to write down the mass and the coordinates. Particle 2 is 1.25 kilograms. And it's located at x equals 1.5, 0.15. And x equals 0.2. So I'm going to make each of these 0.1. Just to give it a little bit of a scale. Okay, so over 1.5 up to, okay. There's another particle. And then the third particle is at 0.2, negative 0.8. Down here. So let's look at the three particles, and, you know, we can use our best intuition to kind of guesstimate where the center of mass would be. It's probably going to be, you know, somewhere like down here in this area. Okay, actually maybe even over here. So let's see how close we get. I'm kind of throwing the dart. Let's see how close we get to that. So let's write down our third. He was 0.75 kilograms, and his coordinates were over 0.2, down 0.8. So we're going to find the center of mass of this system. So the x, so there's some equations for center of mass, right? The coordinate, the vector of the vector location of the center of mass, written in vector form, is going to be mass 1 R1, mass 2 R2, mass 3 R3 vector divided by the sum of those masses. We're going to break that into x and the y. Okay, so it's easier to work with. So we can essentially write two equations. The center of mass x coordinate would be m1r, 1x, right? So let's find the x and the y coordinate using, this form, right? This is only the x form. So let's do the x for now. So our first one was half, 1.25, 0.75, 0.5. And then the r coordinate in the x was 0. And then the next mass was 1.25, and it was at 0.15, x coordinate. And then the final mass, that gives us 2 kilogram total. So the x coordinate of the center of mass is going to be okay, 0.17-ish. So now we're going to do the same thing with the y coordinates. First mass, and the first y coordinate was 0. Second mass, and then the second y coordinate was 0.2. Third mass, and the third y coordinate was negative 0.8. So I'm just going to make sure we keep our negatives in there, right? And then the center of mass, y coordinate, I got 0.175. So over 0.17, down about 1.18. Okay, so It's almost, I was a little bit close, so it's over here, down here, so it's about right here. There's the actual. Okay, pretty close, right? So just so that it makes sense to you, right? You want the math to make sense with the conceptual, understanding. So this is going to be the type of question you'll get on the exam. I consider this to be like a gimme question. This is going to be very straightforward, right? This one you should get. It's going to be at the end of the exam. You're going to be tired, and maybe you should skip ahead and do it first. So, all right, I hope these were helpful, and please reach out if you have any questions. We'll talk again on Monday, and we'll do a live review session. All right, have a good one.